Hello, everyone. Welcome to Friday of week 8. And I did say that I would talk a little bit about additive manufacturing. Typically, in this class, we do a piece on it where we actually do some SolidWorks in the room and get the rapid prototypers running and kind of show you what additive is. But I'm just going to walk you through a few PowerPoints and a video and then show you some SolidWorks to give you a feel what additive is in case you've never heard of it. So I also am planning on adding a class in my program on additive manufacturing and artificial intelligence because it takes AI to run a good optimization of a part, which I'm going to show you. So let me first explain what subtractive is, and then we'll go into additive. So currently, the way we manufacture parts that build things from cars and trucks to planes is we take a large piece of a material. For instance, if I wanted to make this, I would take a large chunk of plastic, pretty big piece, right? Probably rectangular, not triangular. And then I would mill away that plastic to shave it away and shave it away and subtract it from a big chunk. That's called subtractive, right? Machining is often a subtractive process where we take a big chunk of material and we basically whittle it down, carve it down to the shape that we want. Okay? That's subtractive. Additive is just the opposite, where we start with nothing and we literally add material where we want it. That's what a 3D printer is, and I think most of you understand what 3D printing is. Now, what you probably don't understand is what's the value in 3D printing? Why would we want to do this? And what's unique about it? And it is very unique. It is a completely different manufacturing process than we currently have today. Some think it's a giant shift. So let me explain what giant shifts are so you understand what that is. I'm going to get rid of me for a second. I might come back. This is a PowerPoint that I did for the Dead Math Society at Mount Hood. I'm not going to go into all the slides because I believe there's 141 of them, so probably don't want to do that. But I am going to take you through a few of them. So, for example, a lot of you know what snowboarding is. This was a big shift. For years, all we did was ski with two things on our feet, right? And then somebody came up with a snowboard idea, which is one thing on 2 feet, and boom, it's a big shift. So this is kind of a recreational shift, maybe not changing the impact of the world, but let's talk about other shifts. Excuse me. Windsurfing was one too, but here's a big shift, right? Starting with the dial phone, going to some kind of a portable phone. My father actually had one of these. It was really a non-event when he got it to me. I was like, oh, that thing is huge. But then this, clearly, that is a giant technological shift that we're in still. It has changed the course of humanity, the cellular phone. Also, the PC. I again saw this shift, Commodore 64, while I was in college. And again, I thought, oh, my handheld calculator is kind of that cool, right? Absolute giant shift in humanity. And also the handheld calculator, giant shift in humanity. So these giant shifts have taken place, most of them technological, over time. When they actually happen, I actually have this calculator in my office if you ever want to come by and see it, with stress packs in it. One of the first engineering-specific calculators. When the shifts are happening, we don't often see them because it's not, it's not spread out through the world yet. It's in localized places, and a lot of us don't see the full potential. One more shift, CAD, computer-aided drawing. A giant shift, and again, I've lived through this one. I did feel this one because I was the one that introduced CAD to the company I was working at, Peter Kiewit and Sons. For 3 years, I did this manual drawing, and I thought, man, this is slow, takes me forever. And then I saw CAD and saw the complete value of it and had to sell it to my company. They were not big fans. But that's another story for another time. Obviously, from CAD, we get solid modeling, and from solid modeling, we get additive manufacturing. So additive manufacturing allows you to make things that are not manufacturable. Not manufacturable. This kind of lattice structure in this shoe, you cannot make this by hand. It is not manufacturable. But you can make it by additive. This entire shoe is made through the additive process. The bottom, the sole, the support and cushion, and the fabric above, all additive process. So what does this mean to us? This means we no longer have to design with a subtractive mindset. So when I do design, I design from a subtractive mindset. Like if I'm going to design a structure, I think about the lumber that I'm going to use, and that is subtractive. That is a rectangle, a square, maybe some quarter rounds, some different shapes that they subtract out of a tree. I use a subtractive process when I design. I'm not going to design a piece of wood that looks like a wave because they can't manufacture that. They can't manufacture that and be way too expensive to do it, right? Now, with additive, that's not true. They actually are doing additive with wood products. They're doing additive with graphite. They're doing additive with manufacturing fiberglass. They're doing additive with titanium and steel and all materials. It's not inexpensive still. It needs to get larger scaled before it's going to become inexpensive. But the point is they're doing it, and it is now becoming available, and we need to think about designing for additive. It's a whole different mindset because I don't have to think about, oh, I'm going to use a C shape or I'm going to use a square tube or a round. Maybe I want to use some kind of a spider web. Yeah, maybe. All right, so let's go through the additives real quick. Just some of the basic ones. It's exploded, so there are all different kinds. But I'm just going to start with, regular filament additive, which is probably what you've seen, and then go into a little bit of laser sintering and other sinterings that you maybe have not seen. And then just know that beyond that, there are, I'm going to say hundreds, but probably not hundreds. There are tens and tens and tens of of different types of manufacturing with additive. Okay. So I have a couple slides. I went to a conference a couple years ago. This is filament where we just send a material in. This is your typical 3D printer, right? Where you have a coil of material. This says wire coil, but it's a lot of times plastic. Comes up, gets heated, gets liquefied, and then goes down kind of like toothpaste and then solidifies almost immediately enough to keep building, right? So that process looks something like this. I think I will go to presentation mode. Whoops. Just because it'll be a little bigger for you. This is laying down graphite, right? And the head just moves and traces a pattern, and then the table drops. And then the head moves again, traces a pattern, the table drops. A lot of very cool, unique designs. We have one of these in the lab. It's not a graphite machine, it's just a plastic machine. All right. The next one is laser sintering. So this is where we put a powder in, and this is kind of gone gone crazy, this technology, because all of these specialized powders can be put in. Like you can put it in a titanium powder, and what the laser does is it essentially welds it, it sinters it, okay? You can also put polymers in, like this says, and the laser makes it hard, right? It just immediately solidifies it. So, look at a laser machine, and this is with a resin. Essentially, it's curing the resin, right, as it moves along. Then there's multi-laser systems. Here's another sintering machine where this is a powder, and it's going to make some kind of solid. So this could be a steel powder, it could be a titanium powder, it could be an aluminum powder.
So with our filtration, it's all enclosed, it's very protected. Depending on the material, like there's some material can filter the water, and otherwise you can do it. We have a material we use, like a plug in, safe and safe.
I wish I would have let it run longer, because this is going to come out and then wipe and then put a new layer of dust down, the powder dust, and then the laser will trace it again in the exact same spot, sintering it up into a solid. These materials are homogeneous, which means they don't have any voids in them. They're coming out very, very perfect. It's impressive. The kind of structures that you can get from this are very organic structures. So if you design this kind of a thing, you can print it, where that's not really manufacturable. Why are we doing this? Why is this going to be something that we want to work towards in the future? Well, you can do a lot of cool stuff, like this is a fully carbon motorcycle. This is a very light BMX bike. You can see that kind of frame would be impossible to manufacture, but you can do it with additive. Obviously art, I'll call it. All right. So here's an example of why we might want to do this, why the world might want to head in this direction. This is a jet engine made by GE. They call it the catalyst engine. There's actually several of these that have been made now, and let's look at the advantage of doing it additive. What they did is they told engineers, jet engine engineers, to design a jet engine without thinking about manufacturing it. In other words, don't worry about how we're going to build it, just designed it. Okay? So they did it with additive in mind, and they have 25% of these parts are additive, 5% weight reduction. They went 855 parts instead of the high number they had before, so that was a reduction of, I believe, at least 12 parts. And then a 20% lower fuel burn rate by just 25% of additive added to this system, okay? Now, they had more. Let's see, I don't think I have it. I have lots of examples of additive parts. Yeah, so they had another slide where they upped this and reduced the part number incredibly. So GE has warehouses of metal manufacturing additive machines, and they are completely all in additive at this point. They are really moving hard in that direction. This was 2 years ago, and kind of the last slide I'm going to do, and then I'll just show you some other things, and then we'll come back to some really cool parts, okay? Here is the manufacturing bubble in the US. Subtractive, $12 trillion manufacturing sector. Huge. This is a giant subtractive machine that we have in the United States. Here's the 3D printing additive bubble. 5 years ago, this was the size of a pinhead, like just put a spot in this circle. In other words, it essentially didn't exist. 5 years later, we have this size of additive manufacturing. And in 10 years, this bubble will be 4 times as big. It is literally going to take over in their opinion and my opinion, subtractive manufacturing. This is an area you ought to gain as much knowledge as possible, in my opinion. All right, so what is it? We know what 3D printing is, but what is design for 3D printing? Well, design for 3D printing is completely different than the design we do now for subtractive, right? The design for 3D printing is more of just making a basic structure in a software, and this can be SolidWorks, I'll show it to you in a second, and or more robust machines like GE has their own software. But SolidWorks is trying to follow along and gain some market share with their topology. But what you do is you set up a part, then you're going to add loading conditions, and then you're going to optimize it by telling the software what's important, like maybe stiffness and strength and thermal conductivity, surface area, electrical conductivity. Depending on what is important in your part, you tell the software that, and then you say go. And it comes up with versions of your part. Here's a version, here's a version, here's a version of your part. Okay? That is the process. So here's an example. If we need a bracket that mounts up in these 4 spots and also has this support that has a load base on it, what should this bracket look like? You set all this up, you set the material up, you set the load condition up, and then you hit optimize. Now, I don't know if you can hear this gentleman speak, but he will go through some optimization.
And said, I want some solid portions so I can bolt the thing onto my test machine. I gotta have a way to put a load on that. And then the rest of it, you're open to optimize, except I need some access ports to my bolts in, so don't use that space. And then off it went. And said, well, I'd like a little more solid, so it beefed up the solid areas a little more, and then lattices, which is right here, homogenized versions of that. We convert it back with our meshing.
So the first one was a solid version. This is a lattice version.
And now we have a mixture of lattices and solids. We can do true designs where we can look into existing assemblies, those kinds of things. We do multi-physics, which is cool, but now it's multi-physics with lattices. So now not only do you have the option of kind of whether I'm going to wait.
Can you imagine trying to do a physics analysis or a strength analysis on a lattice structure? Impossible. This is artificial intelligence running these kind of iterations for us.
Thermal or compliance as the most important, but it's how dense I want to make the lattice that fits in. And so now I've got this whole family, and this is only kind of 2 variables, right? So we add some more physics, electromagnetics, other characteristics that you really care about, and the space gets n-dimensional, right? And just exploring the design space becomes an issue here. But you can see the kinds of designs that we can look at. In terms of
unbelievable cool stuff, okay? And this is actually happening in industry, and education is just way behind. We're barely teaching it. So again, I'm going to add a course, and we're going to start teaching the basic fundamentals of this next year. So there you go. All right, let's keep going. Look at some parts. Actually, let's look at, here's a video. It's really short, 1:32, on the topology study within SolidWorks.
In design, form follows function. Topology study, built with Simulia technology and fully integrated.
Okay, this is the part they're doing the topology on. So here you can see they've just made a big, heavy, solid part, and it's got loading conditions on it, and they're going to run a topology on it, optimization.
Into SolidWorks Simulation 2018 gives users early insight to optimal part form. Starting with a basic shape, real-life conditions are defined, leveraging SolidWorks simulation fixtures and loads. These can be as simple as a single load or include results from SolidWorks motion or flow simulation. Topology study generates results based on user-defined goals and constraints, like maximizing strength while reducing mass, along with manufacturing controls like symmetry, thickness, and preserved regions to allow for mating components and finish machining. Using the Load Case Manager, Topology study can even account for multiple load cases simultaneously, providing a more comprehensive result based on the full set of conditions the part will experience. Users can generate mesh results for use in additive manufacturing processes, use simulation display.
Okay, so what's important here is it can do this topology, but this is not a subtractive part. You can't make this unless you have an additive process. So this is the design for additive using AI.
To speed feature creation and reuse their setup, copying the study to a new type to validate the performance of their design. Bring form and function together in the design process with topology study.
All right, super cool. Have to say, very cool. All right, let's just go through some more parts. I think you get it. Like I said, I have 141 parts. The Mayo Clinic is doing topology and 3D printing on organs and allowing surgeons to practice before they actually do the surgery on the actual real 3D printed parts of the body that they'll be working on, because they can get that 3D information from scanners, right? So if you go in and have a high expensive scan, it is making a three-dimensional object out of your body, and then that can be printed. They can practice with it. I showed you shoes. Here's a fully functioning jet engine, turbojet. I'll skip this. I'll just go use, this is a bicycle pedal that was fully optimized. Super cool stuff. All these lattice structures and very organic systems come with these different kinds of optimizations, including lattice structures. So here's an example of a lattice structure that you can just apply to a part and make it many times lighter and just as strong. Oh, these are kind of fun. So this is the size of the lattice compared to a quarter. Absolutely tiny lattice structures that can be printed, and I believe this is stainless steel. I talked a lot about the advantages of lattice. These are some titanium parts that I got to look at while I was there. This is a cooler, so fluid goes in here, goes through all these chambers, and comes out here. Incredible, absolutely incredible. Go some more parts because I have a lot of parts in here. This is a 3D printed stick on a backhoe. It's a table. So this is at the Oak Ridge National Laboratory, where they have the largest 3D printers. These are 3D printers, giant, incredibly big 3D printers. Making these kind of structures right here, and this is an aluminum stick with internal hydraulic plumbing. So that eliminates the external plumbing to the stick on a backhoe, and they just run the plumbing right through the inside of the stick. Fascinating. And here's an up-close shot of it. This is some giant laid down, what looks like is welds, the way they do it. And then they just machine up the parts that they need to machine up. More titanium parts, lots of titanium parts. I think I have, let's see if this is it.
So something else you can do,
So this is how it comes out of the printer.
you can integrate hydraulic channels so you can run your fluid through those channels and you don't have to worry.
Yeah, fascinating. I think I have some more here that I actually picked
With
up.
the metals expert. So I think.
Whoops, sorry about that. Oh, this one's cool too. So this, again, this is exactly how it comes out of the printer. You have to clean all the dust off because this is a sintering process and get rid of that dust, but then...
So I don't have your...
Fascinating. Curious. Oh, this is just a ball socket.
With the metals expert. So I think it's about time for y'all to transition to the next group. So you're actually.
Yeah, very cool, huh? All right, here's one of the big printers, giant printers. They do a lot of testing on big prints and cut them up and check the material and see how well it performs. Here's a radiator. Engine parts. I don't know the material in these. There was a lot of titanium. They were really showing that off. This is how the big 3D printer works. Yeah, so it was mostly for welding. Running some giant beads there, like on that stick. I think here's where you can see they cut the material to see how homogeneous it is, how perfect it is. And here they machine it, right? So as it comes out kind of rough, like this, they can machine it up and check how perfect it is. Because if it's like an aircraft part, this has to go through the FAA and get approved. So they'll take some parts, cut them up, and make sure they're perfect inside or homogeneous. All right, I think that's good enough. I think you get it. I could keep going. Like I said, I have 141 slides on additive, and it's important stuff. All right. I showed you the SolidWorks. Did I show you the SolidWorks? Maybe I didn't. So here it is, where you would set up this part. And you'd load it. So we have some size constraints, and then you add some loads to it. And then it's called Ready Optimization. This is in SolidWorks, and you can run it. So once you start to run it, it goes through these design studies. It's going to make some sounds every time it does a study. And you'll see it shift. Its size is shifting around. Now keep in mind, SolidWorks is not a very robust modeler. For it actually to be able to do this, it's pretty impressive. It's reducing material in certain areas based on constraints put on the part by the modeler. That would be us, right? So it's going to run through these iterations and give you all of these different versions of the part based on whatever we put into the software. So super cool. I'm going to stop it because it's just going to keep going and keep coming up with versions. The final version, I think, looks something like that, where it's reduced the material quite a bit. All right. Maybe I'll stop it. Yep. There we go. All right. That's it. I hope you have a great weekend. I might put something up for a discussion posting, but no homework. And the exam will happen over the weekend, I think, for both classes. I'm going to share this video with both classes because I think you all ought to be aware of what's going on in manufacturing, because many of you will end up in that sector. All right, take care.